Hello, my name is Jessica Moran and I am a PhD candidate with the Cooperative Research Centre for Honeybee Products. Today I'm going to talk about my research on sniffing out American Foulbrood. Before I get started, I thought I'd give you a quick overview of the research group that I'm a part of. So within the CRC for Honeybee Products, I am a student at the University of Western Australia in Dr. Julia Grassel's Honeybee Health Research Group. Dr. Grassel's group is a molecular science team and we work on omics using mass spectrometry. We have a particular interest in practical beekeeping, so our honeybee health themes that we work in are bee immunity, biosecurity and nutrition. All of the research we do is done in consultation with local beekeepers, particularly those from Bee Industry Council of Western Australia. If we turn our attention to the honeybee industry of Australia, we are quite spread out. This is a map of the active beekeeping areas in Australia. For scale, this is Texas from the United States and this is France. So you can see that we are a really big country with very remote and diverse beekeeping areas. In Australia, we have 25,000 or so registered beekeepers, but only 1,800 of those are considered commercial. That is, that they own more than 50 hives. So what this means is that of the 670,000 hives that we have in Australia, over 70% of those are actually managed by a handful of beekeepers that each operate 100 or up to more than 1,000 beehives. So you can understand the difficulty that they face with managing and monitoring that many hives closely. And these hives are moved all around the country to maximise honey production. So we have a great deal of movement here in the east coast of Australia and also within Western Australia, but we don't actually have any hive movement into Western Australia, and that's for biosecurity reasons. Western Australia still remains free from European Foulbrood, so we don't want any hives that are potentially contaminated coming into our state. Overall, Australia is also free from the varroa mite. So as you can tell, we do quite well with biosecurity. However, we do struggle with American Foulbrood. So American Foulbrood, or AFB, as we tend to call it, it is Australia-wide. It occurs in all states and territories. We have a policy in mainland Australia where if a beekeeper discovers that they have American Foulbrood in their hive, they then need to destroy that colony. We do not allow the use of antibiotics to control AFB. As you can imagine, this is quite costly for beekeepers. So in just one outbreak in Western Australia that claimed around 200 hives, the beekeeper actually suffered losses of $1.5 million. And this is due to not only having to replace those hives and colonies, but also in the lost opportunity. So losing the honey production and also the ability to fulfill pollination contracts that season. AFB is quite prevalent in Australia. When beekeepers were surveyed, 56% of the respondents said that they'd had a history or a current infection of AFB in their apiary. The prevalence of AFB also seems to be increasing in Australia. So that same survey also found that there was a 5-fold increase in outbreaks between 1971 and 2006. And this is likely to continue increasing as we increase the hive densities, particularly for pollination services in Australia. Unfortunately, only 10% of hives are actually checked for AFB during pollination, which can lead to devastating outbreaks. For example, on the almonds in 2017, we know that a particular company lost 400 hives to the disease, and that's just in one outbreak. So what is American Foulbrood? American Foulbrood is a bacterial disease that can start with a single larvae, but it can eventually kill the whole hive. What happens is the larvae is fed spores of the disease. These spores then germinate and multiply within the larvae as it grows. Eventually, the bacteria break through the lining of the gut and it kills the larvae or the pupa at this stage. And this is where it starts to make a horrible smell as well. The bacteria then liquefy the brood and eventually this dries down into a very spore-rich scale. And these spores are then transported by worker bees to other larvae in the hive. and it gets into the honey, which can then be robbed by other bees, spreading to other hives. And this is what it actually looks like in the hive. On the left are brood that have died of American Foulbrood, and over here on the right, this is a textbook rope test which shows the liquid stage of the disease. Actually diagnosing American Foulbrood in the hive is quite challenging though. It requires the beekeeper opening up the hive completely and looking at the brood for symptoms of the disease. So you can imagine how difficult it is for a beekeeper that is running hundreds or even over 1,000 hives to be able to find the early stages of an outbreak, which might only be 1 or 2 larvae that are showing symptoms. So this is where my research comes in. I was really interested in that foul smell that American Foulbrood gives off, and I wondered whether we could use that smell as a tool for detecting the disease. And I wondered this because all smells are just chemical compounds that are in the air. So when we smell a beehive, what we are actually smelling are the compounds that are associated with honey. So for example, you might smell the eucalyptol in the eucalyptus nectar, or the pinene that are in the wood box, or even the brood and bee pheromones like beta-cis-ocimene. So if 2 hives smell different, they must have a different combination or abundance of compounds. We can visualize this as a volatile profile, meaning the abundance of different compounds in the hive. You can think of this as a bit of a fingerprint for that hive. We can record volatile profiles with a very expensive gas chromatography mass spectrometer. So together with experts, Micah Boland and Gavin, I use this GCMS to look at the compounds in the air around diseased and non-diseased larvae. The data we get from GCMS, it looks like this. Each peak is a different compound, and then we can look up the identity of that compound in a database. These are examples of readouts we were getting from the mass spec. So the volatile profile in black is from a healthy larvae sample, and then the volatile profile in yellow is from an AFB sample. Overall, we identified over 100 compounds in these samples. If we plot these volatile profiles, then we can see that there are distinct differences between AFB over here on the left and non-diseased larvae on the right. So each of these points is actually a sample's volatile profile composed of over 100 compounds. But we wanted to make sure that the volatile profile of American Foulbrood smelled different from other causes of death. So I went back to the mass spec and got some data on the volatile profiles of sackbrood, which is another disease that we have here in Western Australia, and non-diseased larvae that we killed with either heat or cold shock and then let decompose for a day. So with just the volatile profiles, you can see that there are huge differences between the different types of brood, and our model was able to classify the condition of the brood with an accuracy over 97%. So that's being able to identify American Foulbrood just from the volatiles. At some point, I would like to add European Foulbrood to this figure. However, I don't have that data yet because Western Australia doesn't have European Foulbrood. So until the COVID lockdowns ease, I won't be able to go to East Australia and get the samples that I need. So I dove into the analysis further and found that it's only about 30 compounds that are the key to that American Foulbrood volatile profile. They are what we call biomarkers. So this is a heat map showing the abundance of these biomarker compounds in non-diseased on the left and AFB brood on the right. Each row is a different compound, and the abundance of that compound is indicated by colour. Where it's dark, it's highly abundant, and where it's white, it's absent. So these compounds are either in really high abundance compared to the non-diseased, or they are exclusive to AFB. And these are the compounds that if we could use a sensor to pick them up, then we would have a tool for detecting AFB. I should mention that we do know the identity of these compounds, we're just not ready to release that information publicly. So unfortunately, you'll have to wait until our paper comes out to get those compounds. We were pretty excited by these biomarkers and our method for detecting AFB, so we have filed a patent in Australia. The next step though was to make sure that we could still detect them in the hive. So all of the results that I've shown you up until now are from lab experiments where we used larvae and pupae that we had removed from the hive environment. But we needed to make sure that we could detect these compounds in the complex environment of the hive. So we did a field experiment using whole hives. For this field experiment, we actually sampled beehive air instead of just the air around the larvae. And this was set up at the University of Western Australia with the permission of Department of Primary Industries, with great help from our apiary manager, Tiffany Bates. Doing this, we were able to confirm that the biomarker compounds are detectable in hive. That is, they occur in high enough concentrations. They are accurate indicators of the disease, only present when American Foulbrood is present. We got some really neat data to show that the abundance of some of these compounds are correlated with the level of AFB, so we can actually determine how severe that infection is from the volatiles. But what I found really exciting is that we can pick up AFB really early. So some of these biomarkers were detected when there were less than 5 infected brood in the entire hive. So this is some of the data that we collected from those in-hive samples. This is for one compound, which I will call compound X. This is a very simple bar plot that just shows the abundance of that compound, so basically how tall that peak was in our GCMS readings. And then on the x-axis, this is the number of AFB brood that were in the hive. So when there is no AFB brood, we don't see the compound, meaning that it's an accurate marker for the disease. And as the level of AFB increases in the hive, so does the level of this compound. And what we can see is that even when there are less than 10 AFB brood in that entire hive, we're still seeing a strong signal for this compound, meaning that it is a good early detector. So now we are moving forward with our volatile biomarkers to create a portable sensor device that can diagnose AFB from beehive air, effectively a beehive breathalyzer. And this needs to be a practical device that is both sensitive and accurate. It needs to be fast, giving rapid results to the beekeeper, as well as staying cost effective and affordable and user friendly. But we also need to make sure that it's robust, that is, that it can handle getting a bit of honey on it or being bounced around in a truck. The trouble is we haven't found any existing sensor technology for our compounds that is able to tick all of these boxes. So we're going to develop our own sensors. AgriFutures Australia, who is our Rural Research and Development Corporation, are investing over $500,000 into our project. Dr. Julia Grassel has assembled a team of experts from the University of Western Australia, plus me as the PhD student, to develop the sensors and then build and test a beehive breathalyzer prototype. We are hoping to turn this into a commercial product within the next 5 years. And this brings me to the end of my talk. So in summary, we have identified the compounds released from AFB that are specific to the disease and detectable in hive air. This means that we can now use a targeted approach for sensing AFB. And we are starting to develop these sensors for a beehive breathalyzer device. We've always planned to make this into a handheld portable device, but it could also be incorporated into an in-hive remote monitoring system. This device will be a game changer for beekeepers. Instead of having to spend time opening hives, diagnosing American Foulbrood will be as simple as breathalyzing a beehive. Using our device, beekeepers and biosecurity officers will be able to rapidly screen hives for disease, potentially in real time. This will prevent diseased hives from entering pollination sites, keeping bees healthy and beekeepers in business. If you're interested in finding out more about the research or keeping up to date, then the CRC Honeybee Products website is a good starting place. Otherwise, if you have questions for myself or Dr. Grassel, then our contact details are on the bottom of the slide. Thanks very much.